To get human beings to the moon, NASA built a vehicle that weighed over 3,000 tons. This illustrates the core physics problem of spaceflight, the rocket equation. To lift anything into orbit, a launch vehicle must be mostly fuel. In a typical launch, 85% of a rocket's mass is just the propellant needed to lift its own propellant. Because you have to spend so much energy just moving fuel, carrying actual cargo becomes expensive. You are left with a transport system defined by high freight costs, highly delicate engineering, and turnaround times measured in months. Even with modern engineering breakthroughs that allow us to land and reuse boosters, we remain bound by that same chemical equation. If we want to build permanent outposts in deep space, we have to move gigatons of raw materials, and rockets simply cannot scale up their flight rates fast enough to handle that volume. There is an alternative approach to orbit. Instead of forcing a vehicle to carry its massive energy source, the energy source stays on the ground. Right now, we treat every trip to space like a ride in a custom-built car. Building a viable deep space economy requires us to start building the equivalent of heavy freight trains. About 30 years ago, the U.S. government demonstrated that kinetic space launch was possible. At the Lawrence Livermore National Laboratory, researchers ran a program called the Super High Altitude Research Project, or SHARP. They built a massive light gas gun. By using the rapid expansion of compressed hydrogen, they successfully fired projectiles out of a barrel at 3 kilometers per second, roughly Mach 8.8. Funding eventually dried up, but a modern aerospace startup called Green Launch is now reviving this specific technology. Led by one of the original SHARP directors, they are building a new generation of hydrogen impulse cannons. The mechanics rely on mixing hydrogen with helium and oxygen. When the cannon fires, the gases expand rapidly, accelerating the projectile to exit velocities of Mach 17.5. By launching directly at hypersonic speeds, a payload can pierce the atmosphere in under a minute. Green Launch estimates they can complete an orbital delivery in just 10 minutes. The SHARP program demonstrated that high-velocity gas expansion can successfully accelerate projectiles to several kilometers per second. For companies like Green Launch, these tests provide a baseline for scaling that same kinetic energy toward orbital velocities. There is an obvious physical catch. Accelerating from 0 to Mach 17 inside a launch tube subjects the payload to massive forces, peaking at around 30,000 Gs. This is a level of force that would crush most traditional aerospace structures. Another startup, Longshot Space, is approaching this gravitational hurdle from a different angle. Longshot staging mechanics sequentially inject bursts of compressed gas through side ports, squeezing the projectile's angled tail forward. To keep acceleration manageable, they extend the launch tube to 15 kilometers, spreading the curve over time to drop the force to 600 Gs. Even at thousands of Gs, simple electronics have shown resilience. Engineers tested this by taking standard off-the-shelf satellite components, securing them in a small amount of epoxy, and hitting them with a golf club. The solid-state components survived the blunt force impact intact. While 30,000 Gs remains a massive hurdle, tests on epoxy-coated components suggest that ruggedized hardware might endure the shock. It shifts the problem from a theoretical limit of physics to a practical engineering task of packaging and reinforcement. Kinetic launch systems will not be used to send human beings into space, nor will they launch delicate instruments like massive folding space telescopes. But human crews and complex observation satellites make up only a small fraction of the mass required for deep space expansion. To actually industrialize orbit, we need to transport raw cargo in bulk. That means moving tons of water, dense building materials, and liquid rocket fuel. This is where the concept of orbital propellant depots comes in. By placing fuel caches in low Earth orbit, we create the infrastructure that makes space cannons economically viable. The operational reality looks like this. Ground-based cannons repeatedly fire rugged metallic canisters into the sky, punching through the upper atmosphere at hypersonic speeds to deliver bulk propellant into orbit. Meanwhile, traditional chemical rockets do what they do best, safely carrying human crews and delicate equipment off the surface of the Earth. This animated diagram illustrates how the two systems intersect. The crewed rocket arrives in low Earth orbit meanly empty, then links up with a massive propellant depot to fill its tanks with the fuel shot up earlier by the cannons. This approach transitions spaceflight from a boutique, single-launch process into an industrial supply chain capable of reaching Mars. Giant ground cannons won't replace rockets. Instead, they will act as the heavy-duty freight network that carries the bulk mass required to sustain an industrial presence beyond Earth orbit.